Okay, the recording's going. Okay, so new section for today. We're going to talk about section 1.5. Equations of planes, other things about planes, and then there's a category of related questions that we lump together as calling them distance problems. We'll get to that at the end. So here's the first thing we're going to do, talk about the equation for a plane. And in order to find the equation, there's certain information that has to be given. We have to have a well-defined plane. We have to know which plane are we talking about. And so the presumption is that we know a vector that we're going to call the normal vector that is perpendicular to the plane. Normal is a word that sometimes means perpendicular. So anyway, N for normal vector. So that, knowing the normal vector nails down in some sense, kind of which direction the plane, how the plane is angled, if you will. But that doesn't tell us whether we're talking about this plane or that plane or that plane. There's a bunch of planes that are perpendicular to that normal vector. So we also have to say, and I want the one that goes through this point. So we have to indicate a point in the plane as well. And with these two pieces of information, now there's exactly one plane that is normal to that n vector and that contains that x naught vector. Okay, so we have a well-defined plane at this point. Now, to find the equation, let's first recall that an equation is a test. Right? Remember, this is by contrast to parametrizations. Parametrizations are point generators, right? Equations are point testers. So when I say we want to find the equation, we want to find a test. That is, I want to know, if I've got some point x, what's the test? How would I go about testing this point? And what I'm going to propose as a reasonable candidate is keeping in mind that this point x naught is given to be in the plane. The test I'm going to propose for x is that this difference vector needs to be parallel to the plane. So notice if I have if I have a point in the plane, keeping in mind x not also in the plane, then that difference is parallel to the plane. By contrast, if I took a point out of the plane, then this difference would not be parallel to the plane, right? So I get a yes here and I get a no there, as it should be. Okay. So what's bad about this as a test is that it's geometric, right? It's not algebra. It's nice to have algebraic tests because you can plug in and just look at the numbers and see, did it work, did it not work? This is not algebraic. But not hard to see that if that difference is parallel to the plane, then it's also perpendicular. Remember, dot product equals 0 means perpendicular. Well, it means orthogonal, but you remember that whole speech. Orthogonal, then, I'll say, to the normal vector. And this is algebraic. Right? So this is one of the cool things about orthogonality is orthogonality of vectors can be expressed algebraically. So this makes a great test. And this is, in fact, a form of the equation for the plane. Now, you can write it differently if you like. You can kind of distribute the terms there, distribute that dot product, separate the terms. And you can even, if you'd like, give some coordinates, A, B, C, to that normal vector. And then don't forget the x vector. This is the generic vector XYZ, right? Then that dot product works out very simply as just AX plus BY plus CZ. And then don't forget, furthermore, both of the objects on the right-hand side here, highlighter, the normal vector is given, the X naught is given, and so this is just a computation involving stuff that's given that we already know. So that's just some value, D, that's effectively given. So so here's the alternative way to write it. For my own personal preferences, I like this version of the equation of the plane better because it's the objects that participate in the equation are geometrically natural and interesting. I can see the normal vector and how it how it participates in the equation, and the normal vector is geometrically naturally connected to the plane itself. Likewise, x naught, point on the plane, right? And here, it's you can see all your variables, and I guess that's nice, but what's the d? A little hard to see. You can't. It's hard to reverse engineer what the n and the x naught are from that, right? So all else being equal, I like this version better, but they're both fine. Okay, pausing for questions. Do an example in just a moment. Everybody okay? All right. So real quick, I'll point out that not only can you rewrite this like that, but you can kind of turn it around backward, at least on the left side of the equation, if you were to see an equation of this form. Notice you can just peel off the coefficients, and that tells you your normal vector. Neat little trick there. Okay, so here's an example. Suppose I've got 3 points given. Now this is not the way we did things in the what we did previously. Here, no normal vector is given, and yet I appeal to your geometric intuition. If you have 3 points, as long as they're not all in a line or something, right? 3 points defines plane. And so, given these 3 points, and they're not all on a line, by the way, then reasonable question, what's the equation of that plane that contains them? Okay, now here's a broad stroke little bit of advice when you're trying to solve a math problem involving lines and planes and this kind of thing. Try to convert the question to geometry as much as you can. Take the givens, think about them geometrically. Conveniently, they're already points and we don't have much to do there. But also think about your goal geometrically. The question's been phrased as if our goal is to find an algebraic object, an equation. Let's not think in those terms. Let's ask what geometrically would I need to get the equation, and let's think about the geometry. So in order to find the equation, what I need is a normal vector and a point in the plane. And of course now I've got plenty of points in the plane. I've got 3 points in the plane. Plenty to choose from there. But what I don't have is a normal vector. So think of this as I have this geometry given, and I want to find this geometry, and I want to think what geometric moves do I have that can convert that geometry into the geometry that I want. Okay, so that's just kind of a strategy. So thinking it through, now there's various different tricks, tools that we have in our toolbox. Notice that I can pairwise subtract points that are in the plane, and that gives me vectors parallel to the plane. Not what I'm looking for, right? I'm looking for a vector perpendicular to the plane. But I've now got vectors parallel to the plane. And I'm looking for a vector then that's, perpendicular to the plane. Plane is parallel to these vectors. I'm looking for a vector then that's effectively perpendicular to these 2 vectors. And that's a little phrase that when you hear yourself saying, I want to find something perpendicular to 2 given vectors, we flash back and remember that's what cross products do, right? And so this normal vector here, I'm going to compute as a cross product. Specifically a cross product of these 2 difference vectors parallel to the plane. And there we go. Yes?
Wouldn't you get a different normal vector if you flipped like the cross product vectors?
Yeah, you would. Absolutely. Let me talk about that a little bit. And I claim that's okay. Nothing to worry about. Let's suppose that I switched these, did them that way, right? Then what I'm going to get, thinking about properties of cross product, I would get the negative of my otherwise normal vector. So instead of writing down, n dot x equals n dot a, I would instead effectively write down negative n dot x equals negative n dot a. I would get that extra minus sign, but very importantly, that extra minus sign would be on both sides. And then, neat fact. I mean, you're technically right. They are different equations, but they are still equivalent equations because you can get from one to the other just by multiplying both sides of the equation by -1. So yeah, true, absolutely true. You do get a different normal vector, and it also doesn't matter. So, same equation, yes.
How do you know to do B minus A or C minus A?
Doesn't matter. Also, yeah, so you can kind of, there's a lot of choices for how you can come up with parallel vectors. All you really need is two parallel vectors that aren't parallel to each other. So don't do, C minus A and A minus C. That'd be a bad choice, right? But if you want to do C minus A and B minus C, that's cool. Whatever. Or if you want to, pick that as kind of your base point and do A minus C and B minus C. It's all good. Yeah. Okay. Anybody else? Okay, a couple of little examples I want to go through. Oh, yeah, question.
Wait, so will the answer just be the normal vector, or do you have to include the points?
No. So the question is find the equation.
Oh,
so it's
okay.
yeah. So I'm just pointing out that's all over, but the shouting once you get the normal vector, because then it's just this right here.
Yeah.
Yeah, right. Okay. So there's a neat little special case here that I think is cool. It comes up a lot in kind of random little places. If you have a plane where there's no y's in the equation. I'm picking the y's arbitrary. There's an analogous result about x's and z's, but let's just talk about y's. If there's no y's in your equation, right? So ax plus by plus cz, but there's no y's, so that b is just 0. If you ever notice that in your equation, your plane, you can draw a powerful geometric conclusion. It has to be parallel to the y-axis. And this is a handy little bit of geometry to be able to just, boom, instantly notice, casual observation, right? Easy to notice. So I want to talk through why this is true. And here's the idea. Don't forget, these coefficients, you can peel off. They are your normal vector. Right? So normal to the plane is like that. And that's pretty easily seen to be perpendicular to the y-axis. I'm going to indicate the direction of the y-axis by this E2 vector. And don't forget what E2 is. E2 is 0, 1, 0. Right, so real easy to see that this green vector is perpendicular to E2 because we'll look at the dot product. The dot product is easily seen to be 0. So the normal vector is perpendicular to the y-axis, and now geometric appeal, if the normal vector is perpendicular to the y-axis, right, if it's perpendicular, then the plane has to be parallel to the y-axis. And that's just a geometric appeal, but as desired. There you go. So, neat fact. I encourage y'all to think through the equivalent, the analogous, I'll say, version of this for what if there's no x's in your equation? Or what if there's no z's? And it's going to be a kind of a rip-off of this. But think through what has to change and how it becomes just a little bit different, but you can draw an analogous conclusion. Okay. All right. Here's another example. And this is another example of what I talked about before. When you see a question where some things are given, but you want to find something else, if it's phrased as algebra, reconceive it as geometry. Right. So this question is given as I have a couple of equations given to me, and from that I want to conclude a parameterization of a line that is related to those planes in a certain way, whatever. Okay, so algebra given, algebra asked for. So let's think about this geometrically, though. So if I have these two planes given, right, I can interpret from these equations, I can interpret these normal vectors. Right, so I'm taking algebraic information I was given, and I'm inferring geometric objects, namely normal vectors. Likewise with the parameterization. I'm hoping for a parameterization of a line. Let's think now, how do we parameterize a line? Well, to parameterize a line, I need a point that line goes through. Oh, I already have that. All right, that's a given, fine. What I really need then is I need a direction vector to finish up the parameterization of that line. So, yes, algebra given, algebra requested. Reinterpret this as two normal vectors given, one direction vector requested. Everybody see what I did there? Okay. And now you've got of course it's helpful to have a reasonably, interpretable picture of what's going on, but I have these two normal vectors. How am I going to find that v vector? Well, these vectors are perpendicular to their respective planes. Those planes are both parallel to this line, which is parallel to that vector. Therefore, this vector needs to be perpendicular to these two vectors. And then again, cross product. Right. So these two green vectors, you cross them to get the v vector. How we doing? Everybody happy? Okay, now I did a couple of moves here that I want to comment on directly. What I'm going to call a couple of transitivities, kind of. I put that in quotes because I don't want to be precise about this. But going back to this first example, I made the observation that the plane is perpendicular to the normal vector, and the normal vector is perpendicular to the y-axis. And because that was perpendicular and that was perpendicular, I then concluded that those were parallel. Right? So geometric connection, and by their combination, I drew a conclusion about their geometric connection. Okay, so I'm calling that a transitivity of sorts. And then likewise here, I've got, let's see here, these vectors relate to these planes. Those planes relate to that line, and therefore we drew a conclusion about the relationship between these and those. So again, kind of a transitivity. The point I want to make here is heads up, think it through, be careful. Not all statements that one could make that, in words kind of look reasonable are actually true, right? So for example, on the good side, if vector A is parallel to vector B, and if vector B is parallel to vector C, then yes, A and C also parallel. But doesn't it work if one of them is a plane, for example, right? This vector and this plane are parallel. That same plane and this other vector are parallel. But the two vectors, not necessarily parallel. You certainly can't conclude. And again, super tempting. This is parallel to that, which is parallel to that. You'd think parallel was transitive. It isn't. So heads up, think it through. Make sure that your intuition about geometry is right before you run with it. Okay, so this is just, like I say, it's just a warning about landmines. Make sure not to step on those landmines. Here's another good one. These two planes are perpendicular. Right? These two planes are perpendicular. Right? The two purple ones are clearly perpendicular. The two blue ones are clearly perpendicular. And yet, the P and R, no relation. They could be parallel. They could be perpendicular. More likely, they're neither. They're just some random angle in between them. So no conclusion, no transitivity. Everybody good? Okay. Alrighty. Okay, so we've talked about equations of planes. Let's talk about how to parameterize a plane. Keep in mind a parameterization, the different ways to think about it. I like to think of it as a point generator. specifically what we need is position as a function of parameter. This is, in this case, there's two of them. Right now, if you're talking about a parametric line, then it's position as a function of one parameter, singular. Here, in order to make a parametric plane, there's going to be two parameters. But you can see it's an analogous thing. Here's how we do it. You have a point in your plane. You have a vector parallel to the plane, another vector parallel to the plane. And observe that with these objects, if you have a point in the plane and a couple of vectors parallel that point in different directions, right? not dependent, then by scalar multiples, you can go in some sense as far as you want in the v direction, and you can go bad color choice. You know what? Let me redo this in orange. All right, here we go. And then you can go as far as you want in the other direction as well. And so from any starting point in the plane, you can go as far as you want in either direction, therefore to get to any other point in the plane. Right, so altogether, this is going to generate all of these points x in the plane. Everybody see how that works? Notice how it's kind of analogous to a parameterization of a line. It's just that there, instead of one direction to go along the line, there's two directions to go along the plane. Instead of a one-dimensional line being described by one parameter, here we have a two-dimensional plane being described by two parameters. So the analogy is pretty strong. Pretty similar things. Okay, how we doing? Questions? Feel free. Okay, so example, kind of similar to the example we saw previously. 3 points given. These 3 points define a plane. Previously, we looked at how to find an equation of such a plane. Here, different request. Here, we're looking for a parameterization of this plane. Reminder, you want to think geometrically, not algebraically, most of the time. What is a parameterization? What geometrically do I need? Well, here's a parameterization. This is what it looks like. And I need two vectors parallel to the plane. Well, we already know how to do that. We pairwise subtract. Those are parallel to the plane. They go there, per the example above, right above this, and we win. There's our parameterization. What do you think? Everybody good? Okay. All right. Okay. By the way, there's endless different problems that are of this kind of general category. You're given several points that defines a plane that you want to parameterize, or maybe you want to find the equation, or maybe you're given a point in a line and you want to find the plane that contains both, or maybe you're given two lines and you want to find the plane that contains both. Various different things. Identify geometrically what you have. Identify geometrically what you need. And then play games, using the tools in our toolbox to figure out how to get what you need from what you have. Okay. All right. And you'll see a bunch of examples of that on the exercises. All right. Okay, the other thing in this section, distance problems. This is just a collection of various related kinds of questions and the little tricky moves that you can use to answer them. I am going to present these similarly to the way the book does, as techniques, not as formulas. Formulas you're going to forget. It's going to happen. Right? You're absolutely not going to be able to remember just, tracks and tracks of formulas. But tricks and ideas, strategies, cleverness will stick with you for much longer. So, okay, here's what we've got. Suppose we have a point. point X. And suppose we've got a line. Now that line is given parameterized in the sense that I'm given an X naught and I'm given a V there. So given a point in the line, what we want to do is find the distance. So how would I compute the distance from the point to the line? And of course you see that distance is this right here. Now, why, we should note for the record, why is that the distance? Why not this or that or that? There's lots of points on the line that I could, from which I could compute the distance to X. Well, if we made this the definition of the distance to the line, it'd be a pretty weird definition. If you're going to go from the point to the line, you say, how far are you away from the line? I think it makes sense to interpret that as what is the shortest possible distance. Does that make sense to everybody? If you're, offshore, and need to swim to the coast, and you're, how far are you going to have to swim? Well, you're not going to swim at some weird angle, probably, right? You want to swim that shortest distance, presumably, assuming no currents or anything weird like that. Okay, so how are we going to find that distance? Here's the trick. Let vector algebra do a lot of the work for you. I'm going to first think of this vector. What I want is the magnitude, but I'm going to start by thinking of it as a vector. And then I'm going to notice that I can relate that vector to this vector, which is easy to compute. That's just the difference, x minus x naught. And this vector, which is the projection of that w in the v direction. And blue minus orange is that green vector that I want. That's a clever trick. I always thought of it. Somebody showed this to me many years ago. So again, don't think of this as tricks that you should have thought of yourself. It's not what's going on here. Think of this as, these are the clever little moves that somebody else has thought of for us, and we get to take advantage of their ideas and use them for our purposes. So I didn't think of this either. How are we doing? Is everybody on board? Okay. Alrighty. Now, that's one way to do it. You'll notice that this is labeled as 1. There's another really clever way to compute that same distance. That same distance here from the point to the line. This one, not only did I not think of this, I don't know that I ever would have thought of this. This is super clever. Here's the really clever idea. In order to compute that thing we're interested in, we're going to compute something different. Twice. It doesn't seem promising, right? So in particular, let me just show you specifically. I'm going to compute this area of this parallelogram. I'm going to compute it twice. And having computed it twice, I know that those two things are equal to each other. Now I have an equation, and if the thing that I want, namely if the thing that I want, namely this distance, has showed up in one of those calculations, then the fact that I've computed this area twice, and I don't really care about the area, but the fact that I've computed it twice gives me an equation involving the thing that I want, which I can then solve for. This is a really clever idea in math. It comes up lots of different places, where if you want to compute something, don't compute it. Compute something it relates to twice, and then solve. Right? Super slick move. Okay, so details. I claim I've done 2 calculations here. How do these calculations work? The first computation is height times base. So the green height is the distance we're looking for. The orange base is the magnitude of the projection, and we know how to compute projections. So that's one way to compute that yellow area. Yeah? Everybody follow? Okay. Now let's do the other one. What is this other calculation here? This calculation here, I wanted this in purple. This calculation here, I've got a parallelogram after all, And I'm going to look at the projection vector and this W difference vector and realize that those are two edges of that parallelogram. And the cross product, the magnitude that is of the cross product, is a formula that computes the area of that parallelogram. So I have computed this yellow area that I don't care about two different ways, one of which involves what I want. Solve. Everybody happy? Yes?
Will we be given W?
No. So you're given, let's see here, you are given the X, and you're given the line, by which I specifically mean that you're given X naught and you're given V. Right? So, I mean, you have to do that. You have to actually subtract to get the W. And for the record, it doesn't really matter which X naught you pick. I mean, you could use any point anywhere along the line. It doesn't matter. Yeah. Is that cool? Yeah. Yes.
Is there a situation where one method would be better than the other?
That's a good question. I suppose it's, you might get lucky with the geometry with one of them. Like, maybe if for whatever reason that this is a right angle, then that makes the cross product easy to compute, maybe. But then again, it probably makes the other question easier, the other side easier as well. I don't know. They're just different ways to go. I'm not prepared to make a rule as to which one's better in which cases. Yeah. So two different options, though. Okay. All right. Okay. Next question. What if you have parallel planes? Right, so we've got this plane and this plane that is parallel, but let's say a little lower. And how would I compute the distance? Well, first of all, what do I mean by distance? And again, I don't mean that distance or that distance or that distance. Clearly, when we say the distance between two parallel planes, we're talking about the shortest possible distance. And now geometric appeal, hope this seems reasonable, the perpendicular distance is perpendicular to both of the planes. Okay. Or I should say the shortest possible distance is perpendicular to the two planes. Okay. All right, so now just looking at the picture, and again, this is very clever. Don't think of this as something you should have thought of as your own. Think of this as, neat trick that someone has passed down to you. And the trick is this, to realize that if you know the normal vector, that normal vector is pointing in the direction that distance is computed. And in fact, you can just take the component in the normal direction of any difference vector between points in those two planes. Pick any point in the one plane, any point in the other. Right? You look at that difference. Its component in the normal direction is exactly that distance that we want in the first place. And we know how to compute components. Okay. What do you think? Pretty good? Yes?
Do parallel planes have the same, normal vector?
They do. That's right. Yep. Absolutely. Yeah. Yep. Okay, here's the last one. This is also super tricky, super clever. Wish I'd thought of it. Suppose you have skew lines. Skew means that they don't intersect and they're not parallel. It's sort of a worst case scenario when you have parallines. Nothing good happened. They have nothing in common. Not points, not directions, nothing. Okay, so we call that skew lines. How would you find the distance? And again, what do we mean by distance? Well, there's lots of, what is the distance? Well, we mean the shortest possible. And again, geometric appeal, the shortest possible is going to be the one that is perpendicular. All right, shortest possible distance will be a perpendicular to both distance. So, with that noted, the clever move is to realize that those skew lines are contained within parallel planes. And the way you can see them as being in parallel planes is you can take these direction vectors, right? These two direction vectors define at least a class of parallel plane, right? Between the two of them, they define they define a single direction that's perpendicular to both. Right? And so, one of those is going to contain the one line and the other will contain the other line. Right? If I compute this cross product, let's compute the cross product of those two given vectors. Here, let's do it like this. There we go. The cross product there. This cross product, colors again. This cross product is perpendicular to V1, and therefore it's perpendicular to this line, which means that this line is parallel to that plane. And likewise for the other one. So, all over but the shouting at this point, this distance that we're looking for, let's see here, what color did I use? So this distance that we're looking for, the distance between those two skew lines, is, in fact, a distance between two parallel planes, and we know how to compute the distance between parallel planes already. So we reduce this question to a previously solved problem. Everybody good? Okay, tricks galore, yeah.
I have one question. So
Uh-huh.
we have two vectors now, and these two vectors, they may also form another, or determine another plane.
Oh, well, so they determine a whole class of planes, right? So there's a bunch of planes here that are parallel to those two vectors, and I just drew two of them, but let me draw a bunch more of them here. Right, so there's a bunch of these planes that are parallel to both of those vectors, V1 and V2. And I'm just saying, if when you have these two vectors, they're parallel to all these planes, and just find the one. There's going to be one of them that's going to contain that line, and then there's going to be a different one of them that's going to contain this other line. Does that make sense?
Yeah, but for example, is that possible? All the planes that we draw right now, they are horizontal. And
No, they're not horizontal. They're
horizontal. And
okay.
what if we have a new plane that is vertical that includes these both planes?
But see, there can't be though, because this vector, these two vectors over here, they point in what you might call two different directions, and there's only going to be a single direction that's perpendicular to both of them. And any plane that's going to contain both of these vectors, or is going to be parallel to both of these vectors, the normal vector would have to be perpendicular to both of these vectors, and there is only one such direction.
Oh, I see.
Yeah, so your hypothetical doesn't exist. Yeah. Yeah, it's a great question. No, but it's it doesn't nothing to worry about there. I'll say that. Yeah. Okay. All right, so that's a nice little trick move. Okay, so that's section 1.5. We're moving on to 1.7 now. We're going to talk about some different coordinate systems. First, let's talk about what is a coordinate system, and I'm going to start off with the most familiar, the one that you've all seen since middle school probably, and that is the rectangular coordinate system. The idea is this: what we're looking for is a relationship between points, geometric objects sitting inside of the plane, right? Locations, you might say, and their coordinates, namely a pair of numbers that tells me where that point is, right? And so, how does the rectangular coordinate system work? Well, whatever your point is, let's draw the corresponding rectangle like this, and that gives you, by virtue of where those corners land, that gives you, well, an X and a Y, and those are your rectangular coordinates. So, this is just an example of a coordinate system, but notice, given a point, we have a pair of numbers that allows us to identify where that point is. Okay. All right. So, now we are going to talk about different coordinate systems, different ways that you can describe where points are. But I want to take a moment to appreciate rectangular coordinates for certain nice features. The rectangular coordinates are unique. There is only one way to do this. There's only one way to describe, let's say this point right here in terms of x's and y's. Of course, I mean it's so well. I mean, hardly even feels appropriate to say that because, well, how could it be otherwise? Right? Well, we've just gotten used to thinking about rectangular coordinates. We've gotten, let's see how to say this. A little spoiled, maybe. We're so accustomed. We take it for granted that the coordinates are unique. This will not be so in our other coordinate systems, and so sadly, we're going to have to, kind of wean ourselves off of this idea. Here's another thing that's really nice about rectangular coordinates. The algebra just goes one coordinate at a time. If you want to add two vectors represented in rectangular coordinates, cool. Just add their coordinates. If you want to scalar multiply a vector, well, scalar multiply the coordinates. It's all exactly what you would think and hope. And again, it seems almost, well, how could it be otherwise? But again, we're going to find in our new coordinate systems, not so. All right, so that said, be on the lookout for that. Here's our first coordinate system. It's called polar coordinates. I think some of y'all might have seen this before. If you haven't, no problem. So I like to think of this in relation to a function that tells me, given a pair of coordinates, given an r and a theta, we'll talk about what they are in just a moment, but given the two what we call polar coordinates, there is a function that then tells you what the corresponding location is. And the way this works is, given your two coordinates, your two polar coordinates, the theta defines an angle measured off of the positive part of the x-axis, going counterclockwise. And then the r tells you, and I'm going to use some sloppy terminology here, I'll come back and apologize for it in a second. It tells you how far to go in that direction to get to the point you're interested in. Okay, so theta defines a direction, r tells you how far to go in that direction. Now I have to talk about how far business. Technically, how far suggests a distance. Distance is an intrinsically positive thing. R is not. R does not have to be positive. R could totally be negative. And so I just, okay, so if you have a direction theta defined like that, there's your theta direction. If R is positive, then yeah, you go in that direction. If R is negative, you just go backwards. You just go the exact opposite of that direction. So it's exactly what you would think, right? Negative is the exact opposite of positive. But again, technically, not a distance. Distances are, again, intrinsically positive. Let me pause on that for a second. Is everybody on board with what I'm talking about there? Okay, so now how to find what is this function? What are the formulas? Given an r and a theta, what point do I get? And in particular, what are the x and y coordinates of that point? Well, it's a trig thing, and I hope you all remember your trig. Remember, trig is a prerequisite for this course. We're going to use a lot of trig in many places, this being one small example. But that being a right triangle right there, you can see that the x-coordinate is just one side of that triangle, and easy calculation, x from that triangle is r cosine theta. Right, and then of course y is the other side here, that triangle. y is r sine theta. So easy little bit of trig. Everybody good? Okay. So you can think of these as being conversion formulas, and if you know the polar coordinates, then you can use these formulas to compute the rectangular coordinates. And again, I like to think of this, and I'm going to be able to give you a really persuasive motivation for this in a few weeks, probably a month, be a while. But anyway, thinking of this as a function where polar coordinates go in and rectangular coordinates come out is going to be a really useful thing, again, in about several weeks, maybe a month. Okay. How we doing? All right. Okay, first little bit of bad news. Again, they're not unique. I kind of vaguely made reference to this earlier, but here you'll be able to see an explicit example. And let's think about this point right here. It's a point in the xy plane. It has a uniquely defined x and y coordinates. Let's talk about the polar coordinates, though. Let's think about the angle. Well, you could say, well, there's the angle. There's the angle. Some angle theta. Right? There it is. You can just see it. That isn't that just the angle. And then let's suppose that this distance here is 5. Just to have something to write down. Then that r is 5. So here's one of our polar descriptions of that point. R is 5. Theta is whatever that angle theta is. That is one set of polar coordinates for that point. But here's the thing. If I were to take that angle and go around another 2 pi, right? Notice if you go around another 2 pi, then you are left still going exactly the same direction, and you could still talk about, therefore, that being the angle. And we're still going to go a distance of 5 in that direction. And so, well, this then is another perfectly good pair of polar coordinates for that point. And again, the red turned into brown there. That was weird. Okay, so there we go. This extra 2 pi on the angle. Yeah, you have to kind of go around, but it ends up that you pointing in the exact same direction as you have been. So, different polar coordinates for the same point. Yeah? And then it gets weirder because you don't even have to go a full extra turn around. You can also go just a half turn around. If you do an extra half turn, that's an extra pi, right? Now notice that has you going what you might call the exact wrong direction. But if you're going the exact wrong direction, the thing about the exact wrong direction is that if you just go backwards from the exact wrong direction, let's see here, what color am I going to use? Oh gosh, I'll use orange. If I go backwards, in other words, if you let r be negative 5, it still gets you to the same point. Right? So there's kind of 2 different categories of different polar coordinates for a given point. There's what you might call the right direction, plus go around an extra 2 pi as many times as you want. And then there's go the exact wrong direction, plus as many multiples of 2 pi as you want, and then just don't forget you need a negative r to account for the fact that you're going the wrong direction instead of the right direction. So lots of uniqueness problems, you might say. So highly non-unique are polar coordinates. Okay. All right. So bummer. Please do be careful about ambiguities with notation. There's various versions of this, but so for example, if someone describes a point as 2 comma pi over 6, there's a temptation to look at this and say, oh yeah, you know what, that looks like an angle. Because pi over 6, I mean, how often have you seen pi over 6 as a linear distance? Right? But it sure does look like an angle, doesn't it? So it's tempting to say, oh, that must be an angle, and that means that this must be a distance, and therefore this point must be this point. Orange must be this point. Tempting, but uncommon though it may be, there is a perfectly good real number called pi over 6 that could be your y coordinate, and that 2, there's nothing wrong with x equaling 2, so you could very well be talking about that point. Just based on what's written here, I mean, it's at best a good guess that we meant polar coordinates. At best, that's a good guess. At worst, it's a coin flip. Right? So you can't just assume. And now, really, the person who's writing this is the one who should try to remove this ambiguity. And it's very easy to remove the ambiguity. Just indicate what are the coordinates you're communicating. You just say r comma theta equals. And now it's perfectly clear what we're dealing with here. Clearly, as I've got written here, these are the polar coordinates for that point. Okay. And this also removes the ambiguity of, are these r and theta, or are they theta and r? Which is which? And it's tempting to say, well, it'll always be obvious what the angle. What if the angle's 0? Right? Not clear. Okay. All right. Oh, and we're out of time, aren't we? Shoot. All right. So be it. We will pick up here on Wednesday. See y'all later. Have a good one. Yeah.